Miss Amy here. As my homeschool class knows, thermodynamics is not my favorite chemistry module, and I was definitely taking advantage of the fact that we had 2 weeks out of 3 off for spring break and Easter to breeze through the material and let y'all deal with the rest on your own. But I have realized there's a new mathematical technique I failed to talk about. So I want to give a big picture overview of that technique for you right now. As usual, when I'm focusing on concepts in math, I'm going to ignore significant figures just to remove distractions from the key points. But you should always pay attention to those on your homework and your tests. First, let's very quickly review the new symbols we have for this module. Delta H is the energy change or enthalpy change that accompanies a chemical reaction. And for this module, there are subscripts and superscripts that we need to know that can go to multiple symbols. For example, if you see a subscripted F, as here on the delta H, that means it's a formation reaction. So instead of being an energy change for any chemical reaction, delta H sub F is the energy change that accompanies a formation reaction. If you see a superscripted circle or degree symbol, that means we're talking about the energy change that accompanies that reaction at standard conditions. So here we have a subscripted F and the superscripted degree symbol. So this is the energy change that accompanies a formation reaction at standard conditions. It is important to note that standard conditions are not the same as STP, standard temperature and pressure, but instead of 0 degrees Celsius here, we have 25 degrees Celsius and 1 atmosphere. It's the conditions you typically have inside a nice climate-controlled indoor laboratory. Instead of delta H and the various subscripts, you could also have delta S. That's the entropy change that accompanies a chemical reaction. And then finally, we have delta G, which is the Gibbs free energy. And the equation for that is delta G equals delta H minus T, your temperature in kelvins always, times delta S. What's important for this chapter is when delta G is negative, that means we have a spontaneous reaction that's consistent with the second law of thermodynamics. So here's a typical problem you might be asked where they give you delta H and delta S and ask you to solve for a temperature range. And this is something we haven't really dealt with before as far as the math goes. So in this case, delta H is negative 800 kilojoules per mole for a particular reaction, and the delta S is negative 400 joules per mole Kelvin. And we want to know what temperature range will make this reaction spontaneous. First, we bring in our equation. And we take the values from the problem and plug it in. Now, I'm hoping you notice something right away just looking at this. But we have kilojoules in one term and joules in the other. So we're just going to pop over to the side and convert joules into kilojoules. And we're going to take this new equivalent value and put it into our equation instead. Now is where we're going to do the different thing. We want to know when is the temperature range going to be spontaneous? And spontaneous means there's a negative delta G. Well, that delta G could be negative 1, negative 10, negative a million. There's an infinite number of possibilities. We can't solve an equation for that. So what we're going to do is we're going to figure out where's the cutoff point. When is it that negative numbers stop being negative? And that's when they hit 0. So what we're going to do is we're going to solve for when delta G equals 0 and then figure out which side of that will give us a spontaneous reaction. And before we go too far into rearranging this equation, I want you to notice that we have 2 negative signs here in a row. We have minus T times negative 0.4 kilojoules per mole Kelvin. The subtraction sign and the negative sign can cancel each other out, and we can change that to adding the term that's multiplied by positive 0.4 instead of subtracting the term multiplied by negative 0.4. This helps our equation look a little bit cleaner, and now it's time to start rearranging. Remember, we go in the opposite order of PEMDAS when we're rearranging to isolate a variable. So first we see that 2 terms are being added. So we're going to take one of those terms and move it to the other side. To get rid of negative 800 kilojoules per mole, we're going to add 800 kilojoules per mole to both sides of the equation. Now the only operation we have left is that T is being multiplied by that 0.4 kilojoules per mole Kelvin term. So we're going to divide both sides by 0.4 kilojoules per mole Kelvin. We see that our kilojoule units will cancel, and our mole units will cancel, and we're left with kelvins. But notice it's in the denominator of the denominator of the fraction. So it's kind of like saying divided by kelvins, and that actually will flip it up to the top of the fraction. So When we take 800 divided by 0.4, we're going to get 2,000, and then that Kelvin's no longer in the bottom of the fraction, it's just in the top, so we have 2,000 kelvins. But remember, this isn't what we wanted to solve. What we've done is we said, what if delta G was exactly 0, and in that case, T, temperature, would have to be 2,000 kelvins. What we want to do is figure out which side of that 2,000 kelvins do we need to be on so that we'll have a negative delta G, and our reaction will be spontaneous. So to do that, just remember where you started off with the initial equation, but go ahead and plug the 2,000 kelvins in for temperature, and say, what if I made it a little bigger? What if I made it 2001 kelvins? Well, that 2001 kelvins being multiplied by a positive 0.4, so that would make that entire term a little bit larger, and a little bit larger than 0 will be a positive number. On the opposite side, what if you made that 2000 kelvins a little bit smaller? Well, if you made that 1999 kelvins, that's being multiplied by 0.4, so now it's still a slightly smaller number than it was before, and slightly smaller than 0 will be a negative number. Since we know that spontaneous reactions occur when delta G is 0, we do want the negative numbers, so we know the direction we want to go in is making T less than 2,000. Slightly smaller than 2,000 or a lot smaller than 2,000 will definitely make our delta G negative. So our final solution is T must be less than 2,000 kelvins. Anything where that is true will give us a spontaneous reaction. Hope that helps, guys. Thanks.